All right, welcome to today's lecture. We have quite a fascinating and deep topic under discussion for today. This is called Kolmogorov Zero One Law. This is named after the famous Russian Andrei Kolmogorov, who worked in Moscow. He passed away some time ago. He, well, a long time ago actually already. He made a big contribution to mathematical physics, probability, differential equations, also information theory. So one of the kind of great Russian mathematicians. And especially he published, I think it was a book in 1933, written in German, about probability theory and lots of things about these axioms of sigma-algebras kind of are quite often referred to that book from the 1930s. One of the famous theorems is Kolmogorov Zero One Law. That's the discussion for today. What does it say? Kind of the message is that some apparently random things may be non-random. That's kind of draft version of the theorem. And of course, there's a precise version of this. So maybe we'll start with some definitions. And what we will study today is, of course, a probability space. And we use the usual notation, some set omega, some sigma algebra on omega, and some probability measure on the sigma algebra. And we assume that we have some random variables, x1, x2, etc., defined on omega. And what we look about today is about the information contained in this sequence. So we could also think that, okay, this when we look at this, it's an infinite sequence. And we could view this as random sequence. And you could also think that it's an infinite vector. It's a vectored or infinite vector valued random variable, this sequence. But that's maybe too complicated for our purposes now. So it's good to think it's just a collection of random variables indexed by n. We assume they take values in the real line, unless otherwise mentioned. Then we could think of defining what is the information content in this sequence, and then let's define some notation. So let's define X as the sigma algebra generated by this full sequence. So this is the smallest sigma algebra on omega, such that each of these random variables is measurable. We could also define kind of what information can be collected by observing a truncated sequence. That's what we will observe in the real world. So in the real world, we never observe anything up to infinity. We observe it to some finite value n. Okay, when n is assumed to be large, then it makes sense to approximate things by the infinite sequence and ask, okay, what if we get more and more information? What eventually will we know and understand? So this is kind of the first n random variables or first n observations if we think that we observe something over time. Then kind of what Kolmogorov started to think is actually the kind of the reverse thing. What could we observe eventually, or what part of the information in X? Remember, X is now the information contained in the full random sequence. What information related to full sequence is kind of insensitive about the first values of the sequence. So then we define Tn to be the information content on about the sequence if we omit the first observations. And you could think it's missing data kind of thing. What would be then, what sigma algebra would describe kind of if we omit everything from the beginning? So we would like to define T infinity as some sigma algebra. But what would be the sigma algebra that only kind of tells from the tail? So the part of information about the sequence which is insensitive to the finitely many initial values. So assume that you can kind of miss any finite number of data from the initial sequence. What do you still have in the end, in a way? And based on what we already know about measure theory, we are now ready to define this concept. So it should be something which is contained in each of these Tn. Yeah. So if it's contained in T1, T2, T3, so that information should be there. So in a sense, what we want to do, we want to do the intersection of these Tn's. Okay. So now I imagine you pick a set in this intersection. Pick some set A, which belongs to the intersection of Tn. What does it mean then? Then A belongs to sigma n plus 1. It's from that onwards for all n. Yeah. So essentially, no matter how big n you take, A belongs to the sigma algebra that is kind of can be determined without knowing the first n random variables. And that's the kind of intuition here. And that's why we use this definition. An important question is that, okay, we take an intersection of a collection of sets. Is this a sigma algebra? Is T infinity a sigma algebra at all? So we should ask, is this a sigma algebra? And if you have listened carefully so far, you know that the answer is yes. I think we did in the second or first week this exercise that we checked that the intersection, any intersections of sigma algebras is a sigma algebra. And that's why this makes a well-defined sigma algebra as well. Do you have questions about this definition? Maybe, yes.
Can we think this as a kind of decreasing sequence of sigma algebras in a kind of similar way as with the sets?
Exactly. Yes, we can. So let's actually make this point next. So let's maybe make some space here on the right. And then we'll look at this question that what can we say about the ordering of this collection? So first of all, we know that if you look at Tn, so it's the smallest sigma algebra which makes all of these random variables measurable. Yeah. So, and if you compare Tn to x, the full here, so we know that Tn is contained in x for every n. Yeah. Because this is a sigma algebra which makes all random variables measurable. So then, and here we only require a sigma algebra, the smallest sigma algebra, which makes these remaining random variables measurable. So that's why we can we see that this is true, this inclusion. And this inclusion is true for every n. So that's why this intersection is also contained. If each of these is contained in x, so then the intersection is also contained in calligraphic x. That's kind of first inclusion. There are actually many. We will look at this. So we know kind of this type of inclusions, and especially we could write this type of chain of inclusions that T infinity is kind of a very small sigma algebra because it's contained in each of Tn. So we could think that yes, there's a decreasing chain going on, and this is Tn plus 1, this is Tn. And then the chain goes up to, well, T0. Yeah. And T0, if you look at what is T0, so actually this is equal to this X. That's the full sigma algebra generated by the sequence. So this is our first remark. And especially if you write this type of chain, and we have this T infinity being the intersection of everything, so we can also write that this Tn sigma algebras, they are decreasing towards this limiting sigma algebra. Also, we can do another inclusion, namely, if you look at what do we know about xn? So that's the smallest sigma algebra that makes the first n variables measurable. So then, if we have a sigma algebra which makes the first n plus 1 random variables measurable, so then this is a smaller one compared to this one here. And this way we can also continue this sequence. So all of these are contained in X. And if we look at backward, so then what is the smallest one? Well, X1 is there. This is the information content of the first random variable. Here we have more information because we have more random variables. And here we have more information because we have the full collection of random variables. Maybe we could also try to kind of clarify the intuitive meaning. So let's check. I think we can write intuitively that xn is the set of events which can be determined. Let's say the set of events A, which can be determined by knowing these random variables x1 up to xn. And maybe we recall the Dinkins representation theorem, which says that, well, first we could recognize that A belongs to the sigma algebra xn. It means that A is it's equivalent to saying that the indicator of this random of event A is xn measurable. To be precise, we mean xn and then the Borel sigma algebra on the real line. That's what this means. And if you recall Dinkin's identification theorem, we learned that this could be written as the sigma algebra generated by x1 up to xn. We learned the version that something is measurable with respect to sigma algebra generated by a random variable if and only if we can represent this indicator I as a deterministic function, so some function f of x. That's what was the Dinkin's identification theorem, and actually it's possible to prove a vector valued version of it. So think about this x1 up to xn as a random vector. So now something is measurable with respect to sigma algebra generated by the random vector if and only if. This is true for some Borel function. So some Borel function f, which is now a map from the Rn to R. So in this sense, if something is here, if some set is here, so it means that we are looking at an event that we can determine, does the event occur or does it not occur? That's the indicator here. We can determine if the event occurs or not according to some deterministic function f evaluated at this random input. Yeah. So this is the underlying intuition of the what this xn means. Yeah. Then what is the intuition about x? If you look at the full x, so then let's maybe now clean a bit and ask, okay, what about the full x here now? Now we are looking at the full x, which was defined as the sigma algebra of the full random sequence. So intuitively, what it means is the set of events A, which can be determined by the random algebra up to xn, etc. So we go kind of, we look at the full sequence and we ask, okay, what can we determine by the full sequence? And this is a bit more deeper theorem, but it's possible to prove also that kind of infinite version of Dinkin's identification theorem. So it's possible to prove that something is x measurable, and that means that the indicator of A is some deterministic function. Now from the infinite sequence, we take this out, and now we replace here the infinite R infinite, like the infinite random vectors. Okay, this is a bit deeper, so we are not going to prove this and discuss this more, but if you want to look, so you can look in the book of Kallenberg. So that's the book about probability theory. If you want to go further in probability, if you think about doing a doctoral degree in probability or statistics, so you might think of buying Kallenberg 2002, the wonderful probability theory textbook. So that contains kind of all these deeper probability theoretic results that we might, or you might encounter in some cases. Okay, but this is kind of complicated because we need to think about infinite topologies and stuff. So during this master's course, I don't want to go there because it takes a bit of time. So I think the intuitive picture is important. So what this Sigma algebra X means intuitively is the set of events which you can determine as some deterministic function of the full sequence. Okay. And okay. For example, think about this event. Let's think about some event. What would be an example? Let's look at an event omega such that let's say xn is bigger than 0 for some n. No, let's say for infinitely many n. Okay. No, wait. Let's put some n. Yeah, let's put for some n. So what can we say about this type of event? Does this event belong to X? So if you look at this, so it's the event that we can take the union of n, and then we look at the event omega such that, well, here's the input is omega, such that xn omega is bigger than 0. And this is the union of the pre-images, pre-image of the open interval from 0 to infinity. So now we know that this one is this is a Borel set. Yeah, that's in B in the Borel sets, and then that's why this one here belongs to sigma n, sigma xn, and that's why it also belongs to the sigma x1 up to xn. And that's why it also belongs to the full sigma algebra, like this. So each of these belongs to the full sigma algebra X, and we get union of events in X. So then we conclude that A belongs to X as well. So kind of this type of events we can, if we know the full sequence, we can determine for sure if A occurs or if it's not occurring. I hope this makes sense to you. Do you have questions? Very good. Let's clean a bit. And finally, maybe still I might like to chat with you about this T infinity. So now finally, what would be the intuitive meaning of T infinity? So with this understanding, this would be a set of events A, which can be blah, 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 determined by, they can be determined by the full sequence. And also by omitting any finite number of the sequence. Yeah. Okay. That's the intuitive picture of this T infinity. And maybe the next question is, okay, is this is T infinite?
Sorry, should there be T1 and T2 in the T infinite definition instead of X1 and X2 in the blue one below?
I go down.
Yeah. Should there be T1 and T2 instead of X1 and X2, or as in the green definition, there are X's in the definition of X.
These are yes, random variables X. Yeah. And now, yes, these x's are random variables, and these were calligraphic x's. So these were sigma algebras. So
oh yeah, I was confused.
Okay, so yes, it's easy to get confused with this. So calligraphic means sigma algebras, and non-calligraphic means random variables. And
yes,
here, the point is that we are looking at random variables intuitively. Yeah. Okay.
yes, thanks.
Thank you. Okay. So now the question is this? Well, actually, the first question is this T infinity? Does it contain anything? So, is this non-empty? So, is there anything in this sigma algebra? Are we speaking of something, or are we speaking of nothing? So, let's look at the definition once more. If you look at here, it's the intersection of sigma algebras. So, is this intersection? Can it be empty? Or can we be sure that this is non-empty, this collection? Does somebody know the answer? It's not immediately obvious, but it's when you know what to do, it's very easy to check. Because Tn is a sigma algebra, we know that it contains the full set. So because it's a sigma algebra, the full set is contained in Tn. Yeah, every sigma algebra contains the full set. This is true for every n because for every n, Tn is a sigma algebra. So it's true for every n, so that's why omega belongs to the intersection of Tn as well. And the complement of omega is the empty set that also belongs there. Yep. So this is why T infinity is not empty. It contains something. That something is, we know that the empty set and the omega are always contained in this T infinity. And that's why we are actually asking, is it non-trivial? The trivial sigma algebra is the collection that only contains the empty and the omega. This is the trivial sigma algebra and omega, and we ask, okay, is this non-trivial? Does it contain anything else? In this part, actually, let's give this sigma algebra a name. This sigma algebra, T infinity, is called the tail sigma algebra. Of the sequence x1 up to infinity. This is very important because that sigma algebra helps us to understand something very deep later on today, actually. Yeah. So we want to understand what happens in the tail. And our question is now, okay, we know that this is not empty. We have a little bit of an intuitive feeling what it should be, but we don't yet know, does it contain anything interesting?